Bismillahirrahmanirrahim. I am Dr. Asad Ullah, Lecturer, Institute of Numerical Sciences, Cohort, University of Science and Technology. Dear students, welcome to the course of Fluid Mechanics, course code MATH-361, lecture number 12. Today we will start chapter number 2, Fluid Kinematics. In chapter number 1, we have studied different types of fluids and also discussed different types of flows. And we further classify fluids on the basis of Newtonian and non-Newtonian. And then we also prove the Newton law of viscosity and the power law model, and also perform the exercises related to the topics we have studied in chapter number 1. In this lecture, we will try to discuss the following points. Number 1, definition of fluid kinematics. What is fluid kinematics? So we will provide a definition to the fluid kinematics. Number 2, we will discuss methods of describing fluid motion. So how to describe a fluid and its motion in fluid mechanics. So there are two ways to describe a fluid motion. Number 1, the Lagrangian description. Number 2, the Illyrian description. Number 3, we will establish a relation between the Illyrian and Lagrangian descriptions. We will transform both these descriptions to each other, and finally there will be references. Now, what is fluid kinematics? So fluid kinematics is that branch of fluid mechanics which deals with the motion of fluid without considering the actual forces which cause or accompany the motion. The types of forces from the kinematic point of view are the translation, rotation, or rate of deformation. All these types of forces may occur singly or in a combination. It is generally a continuous function in space and time. Here we present a simple example in which a motor car is shown. This picture is taken from the aerodynamics, which reference is given at the footnote. Now, here streamlines are drawn at the motor car. These streamlines shows the geometry of the object and the colors on the car representing different types of pressure forces. Now, how we define fluid flow in fluid mechanics. So for the description of the fluid flow and fluid mechanics, there are two important ways. Number 1, the Lagrangian method. Number 2, the Illyrian method. It means in fluid mechanics, we can describe a flow by using either Lagrangian description or by using Illyrian description. Now, what is Lagrangian method? What is Lagrangian method of specification for the fluid flow? So in Lagrangian method of specification, we fix our attention on a particular fluid particle and follow its motion throughout its course. Suppose that we label the fluid particle by identifying its initial position by x naught, y naught and z naught. At this point, assume that its position vector is r naught and the time t is denoted by t naught, which is normally equal to 0. At any later time t, the same fluid particle moves and occupies the position say x, y, z, whose position vector is r. It is clear that r is a function of time t, but since particles which have initially different positions occupy different positions after the motion is allowed. Hence, the position vector r depends on r naught as well. Thus, the position of a particle is completely specified if the position vector is r and is given as the function of time t and the initial vector r naught is given in equation number 1. Here r is the function of r naught and time t. R is the position vector which is given as xi plus yj and zk. Here I, j and k are the unit vectors along the x-axis y-axis and z-axis respectively, and r0 is the initial position vector. Now, in terms of initial coordinates x0, y0 and z0, equation 1 can be written as r is the function of x0, y0, z0 and time t. We have just replaced the initial position vector by its components x0, y0 and z0. Now, this relation can also be written in the form of equation 2. What we have done, we have just replaced the components of the position vector r in equation 2, that is x component, y component and z component of the position vector r. Now, equation 2 can also be written in the form of equation 3. What we have done here, we have just replaced the x, y and z components in equation number 2 by general functions f1, f2 and f3. Now, this equation number 3 is more general as compared to equation number 2. On the right hand side in figure 2.1, a point is shown whose position vector is r0. After time t, this point moves to the point xyz in space whose position vector is r. Now, how to describe velocity and acceleration in Lagrangian method? So, taking derivative of the position vector r with respect to the time t, we get the velocity vector. That is partial r over partial t at the fixed position vector r0. Further, this is equal to dr over dt because r depends on the time t and the position vector r0. So r0 is fixed, so the partial derivative is equal to the total derivative. Similarly, the acceleration is equal to partial square r over partial t square at the fixed position vector r0, which is further is equal to the total derivative, that is d square r over dt square. So the components of the velocity and acceleration are given as u, v and w in the Lagrangian method of specification, where the acceleration components are ax, ay and az respectively. Since r0 is the initial position vector of the fluid particle, therefore any physical or dynamical property h, that is density, pressure, velocity and acceleration associated with the fluid is a function of r0 and time t, as given in equation number 4. Equation number 4 can also be written in the form of equation 5. We have just replaced the position vector r0 by its components x0, y0 and z0. Now just we have replaced the velocity component v by a general physical or dynamical quantity h to generalize the Lagrangian method of specification. Here we present a simple example for the Lagrangian method of specification in which a dog following omen. Now here we label the fluid particle as a dog because in fluid mechanics we are studying fluids and its properties, so we have just labeled the fluid particle as a dog. Now she can observe the dog's every movement and its reactions towards the environment. She can also track the position and velocity of her dog. Now, what is Illyrian method? In Illyrian method of specification, we select a fixed point in space and observing the fluid particles as it passes to this point. Now, assume that the fixed point in space is x, y and z, and the position vector of this point is r. Thus, any physical or dynamical quantity h, that is density, pressure, velocity and acceleration associated with the fluid will in general be a function of the position vector r of the point in space and the time t as given in equation 6. In equation 6, any physical or dynamical quantity h that depends on r naught and time t. Here r is the position vector as given below. Equation number 6 can also be written in the form of equation 7. So we have just replaced R with its components to get the equation number 7. Now the basic flow quantity in Illyrian description is the velocity. So velocity depends on the position vector r and time t as given in equation number 8. Now we can replace this position vector r by its components x, y and z as given here. Now in components form, equation 8 can be written in the form of equation 9. We have just used the components of velocity, that is u, v and w, and written in the form of equation 9. Now equation 9 can also be written in the form of equation 10. We have just replaced the u, v and w that are general functions in equation number 10, that is f1, f2 and f3. Equation number 10 is more general as compared to equation number 9. In the figure on the right hand side, a point is selected, that is x, y and z in space, whose position vector is r, and the velocity is shown, that is the fluid particle or any object passing to this point has the velocity v, and we are observing its velocity and changes here in its velocity as it passes through this point. Here we present a graphical conclusion to the Illyrian method of specification. In Illyrian method of specification, we choose a fixed point in space and observe the changes or the properties of the fluid as it passes through this fixed point. So, as a conclusion, we say that the properties of any physical or dynamical that is related to the fluid can be written as a function of space and time. Here we present a simple example for the Illyrian method of specification, in which we have chosen a fixed space inside the fluid. Now we are observing the velocity and acceleration of the fishes as it passes to this point. We have to check the velocity and acceleration inside this fixed space as time passes. We have nothing to do to those fishes as that move outside this space. So we are to be focused on this space as the fishes passes to this point. Now, what is the relation between the Illyrian description and the Lagrangian description? First, we transform Lagrangian description to Illyrian description. The primary quantity in Lagrangian method of specification is the position vector r of any individual fluid particle. If x, y, z are the components of r, then we can write in the form of equation number 1, that is the position of any particle in Lagrangian method of specification. So x, y and z are the points in space, and x naught, y naught and z naught are the fixed points in space at time t naught. Now we can change from a Lagrangian system to Illyrian system by differentiating equation 1 with respect to time. So taking derivative of each component with respect to time, we get dx by dt, which is further is equal to the velocity component u, and similarly dy by dt is equal to the velocity component v, and dz by dt is equal to the velocity component w. Here capital F1, F2 and F3 are the derivatives of the small f1 with respect to the time t. Now solving equation 1 for the x naught, y naught and z naught, we have equation number 3. In equation number 3 we have written the x naught, y naught and z naught that are the fixed position vector r naught uh, in terms of x, y, z and time t. Here g1, g2 and g3 are general functions. Okay, now using equation number 3 in equation number 2 to eliminate x naught, y naught and z naught, we get equation 4. In equation 4, capital G1, G2 and G3 are general functions. This equation number 4 is free from the position vector r0, that is x0, y0 and z0, which shows that we are an Illyrian method of specification. Now, let H be some physical or dynamical quantity and Lagrangian method of specification as given in equation 5. Now, from equation 3 and 5 we get equation 6. We have used x0, y0 and z0 from equation number 3 and equation 5 to get equation number 6. Equation number 6 is a general representation for any physical or dynamical quantity and Illyrian method of specification. Here G1, G2 and G3 are general functions. Now we transform Illyrian method to Lagrangian method. The primary quantity in Illyrian method of specification is the velocity field of the fluid particle. F, U, V and W are the velocity components. Then we have equation number 1. In equation number 1, F1, F2 and F3 are general functions and U, V and W are the velocity components. We can now change from Illyrian system to Lagrangian system by writing equation number 2. In equation number 2, we have written the velocity components, that is u is equal to dx by dt, v is equal to dy by dt and w is equal to dz by dt. Now, using equation number 2, in equation number 1, we get equation 3. In equation 3, we have written just the velocity components u, v and w with dx by dt, dy by dt and dz by dt respectively. Integrating equation number 3 leads to three concepts of integration, which can be obtained by using the initial conditions x is equal to x naught, y is equal to y naught, z is equal to z naught at the initial time t naught is equal to 0. Hence, the solution of equation 3 can be written in the form of equation 4. In equation number 4, f1, f2 and f3 are general functions where x naught, y naught and z naught is the position vector r naught. Now, equation number 4 shows that we are in Lagrangian method of specification because we have the fixed point x naught, y naught and z naught and the time t. Let h be any physical or dynamical quantity that is written in the form of equation number 5. So from equation number 4 and equation number 5 we get equation number 6. What we have done, we have just done the integration and by finding the constant of integration using the conditions x is equal to x naught, y is equal to y naught and z is equal to z naught to find the general form of that is given in the form of equation number 6. Equation number 6 is the Lagrangian representation for any physical or dynamical quantity. Following are the references. All these books are provided to the students both in soft and in hard. So in this lecture, I copied the text from the ideal fluid dynamics and some images are provided which are cited at the footnote in that slide. As a conclusion, what we have done in this lecture, we have given the definition of the fluid kinematics and then we go to the Illyrian method of specification and Lagrangian method of specification, that are the flow descriptions in fluid mechanics, and then we further establish the relation between the Illyrian description and the Lagrangian description. That's all. Thank you.